Hello everyone. So let us discuss one more concept on electromagnetic induction. So look at the situation shown in the figure. There is a conducting loop of width L which is kept in a uniform magnetic field which is into the page, and a man is exerting a force F to pull this loop out of the magnetic field region. My assumption is the force exerted by the man on the loop is always constant. I mean, this force is constant. Okay, so when he exerts a constant force on the loop, let us see what happens. Because of this force, initially the loop starts to move towards right, so therefore magnetic flux through this loop decreases, and this induces an EMF and hence current. Because EMF is induced because of decrease in magnetic flux, the induced magnetic field should support this external magnetic field. Therefore, in order to have induced magnetic field into the page, the current should be like this. Correct. This is the direction of induced current. Now, the situation is like this. There is a current carrying conductor which is kept in a magnetic field. So therefore magnetic force should act on this current carrying loop. But however, this arm of the conductor is out of the magnetic field region. So therefore here there exists no magnetic force. And if you look at these two arms of the loop, here currents are in opposite direction. So therefore magnetic force on this is cancelled by magnetic force on this. So therefore there is no force in this direction. Now let us calculate magnetic force on this arm of the loop. So magnetic force is given by Fb vector, which is equal to I into L vector cross B vector. Correct. Now I into L into direction of L vector is j cap cross B into minus k cap. So if you put j cap cross minus k cap, you will get minus I cap. So therefore magnetic force is ILB into minus I cap. So therefore magnetic force is towards left, FB. Fine. So now there are two forces. One is the external force F and the other one is magnetic force FB. Now initially this force is greater compared to this FB, and hence the loop accelerates in this direction only. So therefore its velocity increases in this direction. As the velocity increases, the rate of change of magnetic flux through this loop also increases. That means the magnetic flux through this loop decreases at a faster rate. Even though magnetic flux decreases, but the rate of that decreases faster now. So therefore this increases current I. Okay, because I increases, magnetic force Fb also increases. So therefore initially F is maximum, Fb is less. As the situation continues, F however remains constant but Fb increases. A stage is reached when the force exerted by man becomes equal in magnitude to the magnetic force Fb. At that situation, the loop has reached its maximum velocity, but its acceleration becomes zero because net force is zero now. From in the next situation, if he exerts a constant force, the loop continues to move with a constant velocity only. So there is no further change in velocity of the loop. Correct? Because we have assumed this force is constant. Now the question is, now the loop is moving with constant velocity. There is no change in kinetic energy of the loop. But he should exert the same amount of force again and again. In order to do that, he should lose some amount of energy. But where this energy is going? is not able to increase the kinetic energy of the loop. So energy should appear somewhere, correct? So in order to see where that energy is going, now if you say the resistance of the loop is R, because current I is flowing through this loop, so energy is dissipated as heat in this resistors. Okay, so therefore there is no other chance. So whatever the energy he is losing now appears as heat in the loop. Okay, in effect, he is using this energy to increase the temperature of this conductor. Okay, this happens once the velocity of the loop becomes terminal velocity, that means maximum velocity. Okay, now using this concept, let's find out what is the terminal velocity. Okay, so idea is the rate at which is losing energy is equal to the rate at which that heat energy of this loop is increasing, correct? So therefore I can write the rate at which is losing energy is nothing but the mechanical power of the man, P mechanical, correct, P mechanical must be equal to P, 1 minute, P mechanical is equal to P ohmic. That means P ohmic stands for the ohmic loss in this conductor. Okay, the power dissipated in this conductor. So mechanical power of the man is force into the terminal velocity V into cos theta, but force and velocity are in the same direction, so theta is 0, so it is just F into V. This is equal to ohmic loss, which is I square into R. Okay, so F into V is equal to I means BLV divided by R whole square into R. So if you simplify this equation, you will get the terminal velocity V is equal to F into, so here R square, that cancels with this R, so F into R divided by B square into L square.